Welcome to the Curious Voyager. It's good to have you here tonight, wherever you happen to be. Maybe you're lying in the dark with the blanket pulled up to your chin. Maybe there's a lamp still on somewhere across the room, throwing a soft yellow circle onto the ceiling, and you keep meaning to turn it off, but you haven't, and that's all right. Maybe you're on a train, or a couch, or the passenger seat of a long drive, with the window cool against your temple. Wherever you are, and whatever hour it is in your corner of the world, settle in. You don't have to go anywhere. You don't have to do anything. You can close your eyes right now if you like, and just let the sound of my voice carry you along. I want to talk to you tonight about a photograph. You've almost certainly seen it. It's one of those images that lives somewhere in the back of nearly everyone's mind, even people who've never opened a physics book in their lives. It's a picture of the inside of a nuclear reactor, or rather the pool of water that sits over the reactor's core, and rising up out of that dark water is a glow. A deep, electric, otherworldly blue, not a warm blue like a summer sky, and not a cold pale blue like a winter morning. Something stranger than either, a blue that seems to come from nowhere and everywhere at once, filling the water like light poured into ink, softest at the edges and impossibly intense at the heart of it. And here's the thing about that photograph. Almost everyone has seen it, and almost no one can tell you what it actually is. I'd guess that if I stopped 100 people on the street and showed them that image, most of them would say something like, well, that's the radiation glowing. That's what nuclear looks like. That's the fuel, hot and dangerous, giving off that eerie light. And every single one of them would be wrong. Kind and reasonable and completely wrong. Because that glow is not the fuel. It's not heat. It's not a chemical reaction. It is something far stranger and, honestly, far more beautiful than any of those things. That blue light is, as near as anything ever gets, the closest you will come to watching a rule of the universe being broken. A speed limit, one of the deepest laws we know of, apparently shattered right there in the water where you can see it with your own eyes. Something in that pool is moving faster than it is allowed to move. Faster than light. Now I can feel you sitting up a little, even half asleep. Faster than light. Isn't that the one thing that's supposed to be impossible? Isn't that the whole point? And you're right to feel that. You're right to be suspicious, because here's the little trick I'm going to unfold for you very, very slowly over the course of tonight. Something in that water really is breaking a speed limit. But it's not the speed limit you think it is. It's the wrong law. Hold on to that gently in the back of your mind, and don't worry if it doesn't make sense yet. It will. We have all the time in the world. Before we drift any deeper, let me say one small thing, and then I'll leave you in peace. If you enjoy these slow journeys through the strange corners of the universe, it really does help this little channel to give the video a quiet like, and to subscribe if you'd like more nights like this one. The Curious Voyager is a small, independent thing, and small creators like me genuinely rely on your support to keep these going. And to those of you who've already subscribed, who come back night after night, thank you. Truly, you're the reason I get to sit here in the dark and talk to you about blue light and speed limits and the ghosts that pass through the whole planet. So before you drift off, I'd love to know, quietly, in the comments whenever you get to them, where in the world you're listening from tonight and what time it is in your part of the night. It's a nice thing to imagine, all of us scattered across the dark side of the earth, awake together for a little while. And that's the last I'll ask of you. From here on, you can let go completely. There's no test at the end of this. You don't need to follow every step. You don't need to remember a single number. If you fall asleep before I finish, that's not a failure, that's the whole point. The ideas will still be here when you wake. I'll move slowly, softly, one small mystery at a time. And if your mind wanders off and comes back, you'll find I've barely moved on. I promise not to rush you. I'll try not to make any of this so exciting that it keeps you awake, though if it does, well, at least you'll have learnt something lovely about the universe. A fair trade, I think. So, let's begin, shall we? Let's start with what that blue glow is not, because clearing away the wrong answers is half the pleasure of arriving at the right one. The first thing it is not is heat. When you imagine something glowing, your mind probably goes straight to the familiar picture of hot things glowing. A poker left in the fire until it turns cherry red, the orange coil of an electric stove, the white heart of a candle flame. All of that is real, and it even has a name, and we'll cross paths with it later in our journey, but that is not what's happening in the reactor pool. The glow there is not because the water is hot, or because the fuel is hot, though the fuel certainly is hot. If heat were making that light, the colour would tell a completely different story. Hot things glow red first, then orange, then yellow, then white, and only at truly ferocious temperatures do they begin to edge toward blue. And nothing in that pool is anywhere near that ferocious. The water, remarkably, stays quite cool, cool enough that engineers can and do stand right beside it. Whatever is making that blue, it is not warmth pouring out of something scorching. The second thing it is not is a chemical reaction. When you think of light coming out of chemistry, you might picture one of those glow sticks you snap at a concert, the ones that shine for a few hours with that soft plastic light. Snap the little tube inside, two chemicals meet, they react, and the energy of that reaction comes off as a gentle glow. Fireflies do a version of the same trick, mixing chemicals in their bellies to light up a summer field. But that's not what the reactor pool is doing either. There's no reaction between substances there, no fuel meeting oxygen, no two chemicals combining and releasing their light. The blue is not coming from anything mixing together. The third thing it is not, and this one is the sneaky one, because it fooled some very clever people for a very long time, is fluorescence. Now, fluorescence is a wonderful thing, and you've seen it. It's what makes a white shirt blaze under the ultraviolet lights of a nightclub. It's what makes certain rocks glow strange colours under a special lamp. It's what makes highlighter ink almost seem to shine on the page. In fluorescence, a material drinks in light of one colour, usually an invisible colour like ultraviolet, and spits it back out as light of another colour that your eye can see. The material itself, its very substance, decides what colour comes out. Change the material, and you change the glow. And for years, when people saw that faint blue light coming off radioactive things, that's exactly what they assumed it was. Some kind of fluorescence, the stuff itself glowing the way a mineral glows under a lamp. That guess was reasonable. It was also wrong, and part of our story tonight is the tale of the patient man in Moscow who proved it wrong. But we'll get there. And the fourth thing that blue light is not, the biggest misunderstanding of all, is the fuel itself glowing. This is the one nearly everyone believes. The idea that radioactive material is somehow just luminous, that it shines the way a glow in the dark star on a child's ceiling shines, that the danger and the glow are the same thing. That the blue is radiation made visible in some direct and simple way. It is such a natural thing to believe. And it isn't true. The uranium isn't glowing. The core isn't glowing. If you could somehow lift the fuel out of the water and hold it in the empty air, it would not shine. blue at all. The blue only appears in the water. Take away the water, and you take away the light. That's a strange thing to sit with, isn't it? The glow needs the water. The water is not just the thing the light shines through. The water is part of how the light is made in the first place. So if it isn't heat, and it isn't chemistry, and it isn't fluorescence, and it isn't the fuel itself shining, then what on earth is it? What is making that deep, still, electric blue? Here is the honest answer, and I'm going to give it to you plainly now, and then spend the rest of our night gently unfolding what it means, because the plain version sounds impossible until you understand it. And understanding it is the whole pleasure. That blue light is being made by tiny charged particles thrown out of the nuclear fuel at enormous speed, and those particles are travelling through the water faster than light can travel through the water, and when something charged moves through water faster than light moves through water, it leaves a wake of light behind it. A shockwave. And that shockwave piling up and spreading out through the pool is the blue you see. Now I know. I know exactly what just happened in your half-asleep mind, because it's the most natural objection in the world, and it's the doorway to everything wonderful about tonight. You heard me say something is moving faster than light, and every instinct you have said, no, that's the one thing that can't happen. Nothing goes faster than light. Everyone knows that. Einstein said so. It's the great cosmic rule. So either I've got it wrong, or the universe has got it wrong, and neither of those feels very likely. So let's slow all the way down here, because this is the heart of the confusion, and it's a confusion worth dissolving completely. Let me pull the two ideas apart, very gently, and lay them side by side, and once you see them next to each other, the whole thing stops feeling like a paradox and starts feeling like the most natural thing in the world. There are, it turns out, two different speeds hiding inside the phrase, the speed of light. Two of them. And almost all the confusion in the world about this blue glow comes from not knowing there are two, from squashing them together into one number and one rule. So let's separate them carefully and give each one its own place to rest. The first speed is the famous one, the one Einstein built his whole picture of space and time around. This is the speed of light in a vacuum, in truly empty space, with nothing in the way at all, no air, no water, no glass, nothing. Just light, flying free through emptiness. And that speed is a very particular number. It is about 299,792 kilometers every single second. Nearly 300,000 kilometers a second. It's such a staggering number that it barely means anything to say it out loud. Light in a vacuum could circle the entire Earth about 7.5 times in the time it takes you to say the words 1 second. That is the speed we usually mean when we say the speed of light. Physicists give it a name, a single letter. They call it c. Just c. A small, quiet letter for the fastest thing there is. And here is the great rule, the true and unbreakable one, the one Einstein really did give us. Nothing that has mass, nothing made of stuff, nothing you could ever weigh or hold or point at, can ever reach that speed. Not almost reach it. Not nearly. It can never get there. You can push a particle faster and faster and faster, pour more and more energy into it, and it will climb closer and closer to C, but it will never, ever arrive. The speed c in empty space is a wall that nothing material can touch. That rule is real, and it is not being broken tonight. Not in the reactor pool. Not anywhere. Hold that firmly. Nothing with mass reaches the speed of light in a vacuum. Full stop. That law stands, untouched, all night long. So keep that first speed in one hand. C, in a vacuum, nearly 300,000 kilometers a second, forever out of reach for anything made of matter. Now let me put a second speed in your other hand, and this is the one almost nobody thinks about, and it's the one that unlocks everything. Because light does not always travel at sea. Light only travels at that full, magnificent top speed when it's moving through nothing at all, through pure empty vacuum. The moment light enters something, the moment it passes into a material, into air, into glass, into water, it slows down. It genuinely actually slows down. Not because anything is stopping it exactly, but because as light moves through a transparent material, it's constantly interacting with all the atoms it passes, being absorbed and re-emitted, jostled and passed along, and the sum total of all that jostling is that the light gets through more slowly than it would through empty space. The busier the material, the more the light slows. Physicists have a lovely, simple way of measuring how much a given material slows light down. They give each transparent thing a number, and the number tells you the factor by which light is slowed. They call it the refractive index, and they write it with the letter N. For empty space, for a perfect vacuum, that number N is exactly 1, because a vacuum doesn't slow light at all. Light in a vacuum travels at c divided by 1, which is just full speed, as it should. But for water, that number N is about 1.33, roughly a third bigger than 1. And what that means is that light travelling through water moves at c divided by 1.33. Let's actually do that gentle piece of arithmetic together, slowly, because the answer is the whole point. Light in a vacuum goes about 299,792 kilometers per second. Divide that by 1.33 and you get something around 225,000 kilometers per second. So light, passing through water, dawdles along at only about 225,000 kilometers a second, which is still fast, unimaginably fast, but it is noticeably slower than its top speed in emptiness. It's about 3/4 of the vacuum speed. Light in water travels at roughly 3/4 of the pace it keeps when it's out in the open, with nothing in its way. Sit with that for a moment. In water, light slows down. It drops to about 3/4 speed. It's like a runner who sprints flat out across an open field and then has to wade the same distance through waist-deep water. Same runner, same effort, but the water holds them back. They can't move through the pool as fast as they moved across the grass. Light is like that. In the open vacuum, it flies at c. In the water, it wades at 3/4 of c at around 225,000 kilometers a second. And now, only now, with those two speeds resting one in each hand, we can go back to the reactor pool and the impossible sounding thing I told you and watch it stop being impossible. Because here is the quiet, elegant heart of it. When a tiny charged particle gets flung out of the nuclear fuel, it comes out fast, ferociously fast. Nearly, but never quite, at c, the full vacuum speed. And that particle, remember, has mass. It's made of stuff. So it obeys the great rule perfectly. It never reaches c, it never touches the vacuum speed of light. That law is honored completely. But that particle isn't flying through a vacuum, it's flying through water, and light in the water isn't going at c anymore. Light in the water has been slowed down to about 3/4 of c, to that dawdling 225,000 kilometers a second. And the particle? The particle is under no such restriction. Nothing slows the particle down the way the water slows the light. The particle came screaming out of the fuel at very nearly the full vacuum speed, and it keeps very nearly that speed as it enters the water. So you have a particle moving at almost c, and light around it moving at only about 3/4 of c, and the particle, quite genuinely, quite really, is moving faster than the light in that water. Do you see it now? Do you feel how it slips free of the paradox? The particle is not faster than light in a vacuum. It never was, and it never could be. That law is untouched, but it is faster than light in the water. And those are two completely different speeds, and only one of them is forbidden. The wall that nothing can pass is the vacuum speed. C, the speed of light in the water, is a much lower, much gentler limit, and there is nothing at all in the laws of physics that stops a fast particle from beating it. Beating the speed of light in a material is perfectly allowed. Beating the speed of light in a vacuum is what's forbidden, and the particle in the pool only does the first one. It never comes close to the second. That's the wrong law reveal. That's the trick I promised you at the start, when I said something in the water is breaking a speed limit, but not the one you think. The speed limit everyone imagines is being broken, the great cosmic C, is not broken at all. It stands as firm as ever. The speed limit that actually is being broken is a smaller, local one, the speed of light through water, and breaking that one is no crime. It happens all the time. It's happening right now, in reactor pools all over the world, every single second. I want to linger here, because this is the pivot the whole night turns on, and it's worth being sure of before we drift onward. There's a proper name for the slower speed, the one the particle is actually beating. Physicists call it the phase velocity of light in the medium. That's a mouthful, and you can let the phrase float right past you if you like, but the idea underneath it is simple. It just means the speed at which the light waves themselves travel through the water, that's slowed down, 3/4 pace, the c divided by n we worked out a moment ago. That's the speed the particle outruns. Not c, never c, just the phase velocity, the wading speed of light in the pool. And notice what this immediately tells us about that fourth wrong answer from earlier, the one about the fuel itself glowing. Remember how I said, take away the water, and you take away the light. Now you can see exactly why. If you pulled the fuel out and held it in empty air, or in a vacuum, the particles would still come flying out just as fast. But in a vacuum, light travels at its full speed c, and nothing with mass can catch it, so no particle could ever outrun it, and there would be no wake, and no glow. The blue depends completely on the light being slowed down. It depends on the water. No slow medium, no glow. The medium isn't just something the light passes through. The medium is the thing that slows light down enough for the particle to beat it in the first place. That's why the light lives in the water and dies in the vacuum. That's why the pool glows and the bare fuel wouldn't. And isn't that a strange and lovely inversion of everything you'd have guessed? You'd think a vacuum, empty space, the freest possible place, would be where the most exotic light shows happen. And it's the opposite. In the perfect emptiness of a vacuum, this whole spectacle is flatly impossible, because their light runs at its untouchable top speed, and nothing can gain on it. It's precisely because the water gets in light's way, precisely because the water is crowded and slows light down, that the miracle becomes possible. The obstruction is what makes the magic. The imperfection is the whole point. You need the water to muddy light's stride before a particle can ever get ahead of it. I find something deeply calming in that, honestly, and I hope you do too as you're lying there, So much of what we're taught about the universe sounds like a list of iron prohibitions. You can't go faster than light. You can't reach absolute zero. You can't build a perpetual motion machine. No, no, no. And here is this glowing blue exception that turns out not to be an exception at all. Just a case of two different speeds wearing the same name, and the moment you separate them, the impossible thing becomes ordinary and allowed and even beautiful. Nothing was broken. Nothing was cheated. The rule was never bent. We just had two speeds tangled up under one word, and untangling them dissolved the whole mystery. So let me gather up where we've drifted to, softly, the way you might smooth a blanket before settling deeper into it. That blue glow in the reactor pool is not heat, the way a hot poker is not what's shining there. It is not chemistry, the way a glow stick is not what's happening in the water. It is not fluorescence, not the water drinking one colour and giving back another, though clever people believed that for years. And it is not the fuel itself glowing, because take the fuel out of the water and the glow would vanish. What it is, instead, is light being made in the water by tiny charged particles that come out of the fuel at almost the speed of light in a vacuum and then find themselves in water, where light itself has been slowed to only about 3/4 of that speed. And so the particles quite genuinely outrun the light around them. Not the forbidden vacuum speed, which they never touch, just the local, slower, perfectly beatable speed of light in the water. There are two speeds. There have always been two speeds. Light in a vacuum, c about 299,792 kilometers a second, the great unreachable wall for anything made of matter. And light in water, slowed by the refractive index n of about 1.33 down to roughly 225,000 kilometers a second, about 3/4 as fast, and a wall low enough for a fast particle to leap right over. The particle honours the first speed perfectly and beats the second one easily, and in the beating of it, in that small local speeding, the blue is born. And now you're probably beginning to wonder, if the particle is outrunning the light in the water, what does that actually look like? Up close. What happens to the light when something charged tears through it faster than the light itself can travel? Because it's one thing to say the particle wins the race. It's another to understand why winning a race against light should leave a glowing blue wake spreading through a pool. And here's where it gets truly lovely, because the answer is something you already understand in your bones, something you've heard with your own ears on a summer afternoon, something to do with a sound in the sky and the shape it leaves behind it. There's a wake that forms behind the particle, a cone of piled-up light, and it has an almost exact twin in the everyday world, a wake you already know. But that, my friend, is where we'll go next, once you've had a moment to let all of this settle. So stay with me, wherever you are, with the lamp still glowing or the window cool against your cheek, and let those two speeds drift apart in your mind like two boats easing away from the same dock. And we'll follow the wake of light together, slowly, into what comes next. So, let's talk about the threshold. Because before we get to the sonic boom, before we build the cone, before we understand why the angle of that glow is secretly a speedometer, there is a very natural question to sit with first. And it goes like this: does every particle in that reactor water glow? If something is charged and moving, does it automatically make Cherenkov light the moment it enters the pool? The answer is no. And the no is interesting. There is a doorway, a minimum speed, a line the particle must cross before any light appears at all, and below which the water is perfectly, completely, stubbornly dark, no matter how many particles are moving through it. Think of it this way. Imagine you are standing at the edge of a very still pond, and you are flicking small stones into it. If you drop a stone in gently, almost without speed, it lands and makes ripples that spread out in all directions, circles within circles, and the stone sinks slowly into the center of its own disturbance, never running ahead of any wave it makes. The stone and its ripples stay together, more or less. The stone is not fast enough to outrun itself. Now imagine you throw the stone hard, skimming it across the surface at some speed. Still ordinary ripples, still slower than the stone, still trailing behind. But now imagine something moving through the water, not across it but through it, at a speed that genuinely, cleanly exceeds the speed at which the disturbance can propagate. That is when something new happens. That is when the circles stop being circles and start stacking up into a shape. But first, you have to be fast enough. You have to actually beat the speed at which the medium carries its disturbance. And for Cherenkov radiation, that means the particle's speed has to exceed the phase velocity of light in the medium, that c divided by nn, that roughly 225,000 kilometers a second in water we talked about before. As long as the particle is slower than that, it is like the slow stone. Ripples, yes, but no cone. No coherent glow, no blue. The condition has a clean way of being written. The particle's speed, divided by the speed of light in vacuum, has to be greater than 1 divided by the refractive index. Physicists call that ratio the particle's speed divided by c. They call it beta, written with the Greek letter. And the condition for Cherenkov light to appear is simply that must be greater than 1 over n. In water, where n is about 1.33, that means has to exceed about 0.75. The particle must be moving at more than about 75% of the speed of light in vacuum. Below that, nothing. Above it, the blue begins. Now, what does that actually mean for the particles in a nuclear reactor? An electron in water needs a kinetic energy of roughly 0.26 million electron volts. Physicists write this as about 0.26 MeV to hit that threshold, which sounds very precise, and it is, but what it really means in practice is this: the particles that come out of nuclear fission and its decay products, the beta particles. The fast electrons ejected from unstable nuclei as they settle towards stability, those particles routinely carry energies well above that threshold. Not barely above it. Comfortably above it. Easily, routinely above it, the way a car doesn't just barely cross a speed limit sign, but rockets past it without effort. So yes, in the reactor pool, the beta particles from fission products glow. They have the energy. They cross the threshold without strain, and the light follows. But a slow particle, a thermal neutron drifting along at modest speeds, the kind of particle that is also abundant in a reactor, does not glow. A thermal neutron is moving far below the threshold, and even a fast proton, which is much heavier than an electron, needs much more energy to reach the same fraction of the speed of light. So the glow is selective. It favors the light, fast, charged particles. The beta electrons are the primary architects of the blue in that pool. And there is something quietly beautiful in this selectivity. The reactor water is not simply lit up uniformly by everything moving through it. It is lit up by the fast ones, the ones that have crossed a particular speed limit, and only those. The darkness and the light in that pool are not random. They are a record of which particles were fast enough. All right. Now let's build the cone. Close your eyes for a moment and imagine a charged particle entering the water. Not the whole complicated quantum picture, just a particle, a small, fast thing, moving in a straight line. As it moves, something happens to the water around it that is very gentle and very local. The electric field of the particle, as it passes by, very briefly perturbs the water molecules near its path. It nudges their electrons very slightly toward or away from the particle, distorting them for just an instant before the particle moves on. Physicists call this polarization of the medium. Now, when that polarization relaxes, when the water molecule snaps back toward its normal arrangement as the particle has already passed, it emits a tiny wavelet of electromagnetic radiation, a little sphere of light spreading outward from the point where the polarization happened, growing at the speed of light in water. So picture the particle at position 1. It polarizes the water there. A spherical wavelet is born at position 1 and begins expanding outward at roughly 225,000 kilometers a second. The particle keeps moving. Now it's at position 2, a short distance further along. Another polarization, another spherical wavelet born at position 2, spreading outward. Position 3. Another wavelet. Position 4. 5, 6, all along the particle's path. At every point, tiny spherical wavelets are being born and expanding outward. Now here is the key question. What do all those expanding spheres look like together? If the particle is moving slowly, slower than light in the water, then by the time the particle reaches position 2, the wavelet from position 1 has already expanded farther ahead of the particle than the particle has travelled. The particle is always lagging behind its own wavelets. The wavelets spread outward in all directions, and there is no particular direction they all happen to be going. They don't add together in any organized way. The light from different points along the path is out of phase, scattered, and largely cancels itself out. No glow. But now make the particle faster than the phase velocity of light in the water. The particle reaches position 2, while the wavelet from position 1 has only expanded a small amount. The particle is outrunning its own wavelets. It is leaving them behind, and here is what happens when you draw it out. All those little expanding spheres, trailing behind the particle's path, they all share a common tangent surface. There is a cone-shaped surface, like the surface of an ice cream cone laid on its side, with the particle at the tip, where all those little spheres just barely touch each other. They are tangent to the same cone. And at that cone surface, all the wavelets from different points along the path are arriving in phase, all lined up, all adding together coherently. That coherent addition is the glow. The wavelets reinforce each other along the cone surface and cancel everywhere else. The light is concentrated, organized, directed, a shockwave of light rather than a fog of it. You have seen this before. Or heard it, rather, when a supersonic aircraft exceeds the speed of sound in air. The same geometry unfolds in pressure waves. The aircraft is the fast-moving source. The pressure waves it generates spread outward as spherical disturbances at the speed of sound. When the aircraft is moving faster than sound, it outruns those pressure disturbances, and they pile up into a cone behind it. A Mach cone, and the surface of that cone is what reaches you as the sonic boom. Not a continuous sound, but a concentrated line of coherent pressure, everything stacked up at once. The Cherenkov cone is precisely this, translated from sound into light. Not a boom of pressure, but a boom of electromagnetic radiation. A flash of coherent light, concentrated along the cone surface, radiating outward at a particular angle from the particle's path. And there is another twin, even more serene to think about. A speedboat on a still lake, moving faster than the ripples it makes, leaves a V-shaped wake behind it. Stand on a shore and watch a fast boat go by. The wake spreads from both sides of the hull in that distinctive wedge shape, and the angle of the wedge depends on the boat's speed relative to the water's wave speed. A faster boat makes a sharper, more pointed wedge. A slower boat, still faster than the waves, makes a wider one. The shape encodes the speed. This is the Cherenkov wake. Same geometry, same encoding of speed into angle, translated from ripples on water into a cone of light moving through water. So the particle is the boat, the wavelets are the wake, and the angle of the cone is a record of how fast the particle was going. Which brings us to the number. The Cherenkov angle, the angle between the particle's path and the surface of the light cone, has a precise, elegant formula. The cosine of that angle, call it theta, is equal to 1 divided by n times. Or if you write it out, cos equals 1 over n times, where n is the refractive index of the medium and is the particle's speed divided by c. Take a moment with that. It's worth letting it land slowly. The angle depends on is the particle's speed. So the angle of the light cone directly, mathematically, quantifiably tells you how fast the particle was moving. It is a speedometer written in geometry. For a particle moving so fast, it is nearly the speed of light, very close to 1, an ultra-relativistic particle. In water, where n is about 1.33, the formula gives us the cosine of theta equal to 1 over 1.33, which comes out to about 0.75. And the angle whose cosine is 0.75 is about 41 degrees. About 41 degrees. That is the opening angle of the Cherenkov cone in water for a very fast particle. Roughly the same angle as the corner of one of those sticky triangular notepapers if you folded it point to corner. Not a wide cone, not a narrow needle, something between. Something specific. Something you could measure. And for a slower particle, one that barely clears the threshold, one moving at just a hair above 75% of the speed of light in vacuum. The cone is much narrower. The cosine of the angle is closer to 1, meaning the angle is closer to 0, meaning the light radiates nearly straight forward along the particle's path. A sliver of a cone. And for a particle moving below the threshold, cos would have to be greater than 1, which is mathematically impossible. The cosine of any real angle is never more than 1. Which is the geometry's polite way of telling you there is no cone, no radiation, nothing. The threshold condition is built right into the formula. There is a shape hidden in the glow, and the shape is a number. The blue pool is not just a blue pool. It is a display, and if you know how to read it, every cone of light scattered through that water is showing you how fast its invisible parent particle was moving. But let's not rush on. Let's linger here for just a moment, because there is something I want to make sure settles in properly before we move on. The particle is traveling through the water. At every point along its path, it nudges the water's molecules, polarizes them, very gently, very briefly. Each nudge radiates a wavelet. The wavelets from all those nudges expand outward at the phase velocity of light in water. And because the particle is moving faster than those wavelets, it is always ahead of the expanding spheres it makes. All those spheres, trailing behind it in a line, share a common surface, the cone. At that cone surface they arrive together, in phase, reinforcing each other, and there the light is born. It is a wave phenomenon. It is coherent addition. It is the same underlying music as the sonic boom and the bow wave, played in a completely different key. And now, after sitting with the shape and the angle, a very reasonable question creeps in. A question you might be thinking right now, resting wherever you are. Why blue? Why not red? Why not green? Why not a soft warm amber like a candle? Why does this particular effect produce that particular color, that deep, almost electric blue, sitting just at the edge of the visible spectrum before it tips over into the ultraviolet, where your eye can't follow? The honest answer has to do with something that is almost never explained properly in the short versions of this story. The blue has nothing to do with water being blue. Water does have a very slight tendency to absorb red light and scatter blue, which is partly why the ocean looks blue on a sunny day, but that is not why Cherenkov radiation is blue. If you were looking for that simple answer, this is the place to gently set it down. The real reason is in the spectrum of what the Cherenkov mechanism produces. Cherenkov light is not a line spectrum. A line spectrum is what you see from a neon sign or a sodium lamp, specific discrete colors, specific wavelengths, the fingerprint of particular electronic transitions in particular atoms. Fluorescence has a characteristic color that depends on the fluorescing material. But Cherenkov radiation is not like that. It does not care what atoms are in the water. It is not the water's atoms emitting light at their preferred wavelengths at all. Cherenkov radiation is a continuous spectrum. The particle's passage through the water produces light at many different wavelengths simultaneously across a broad range, from the infrared all the way up into and beyond the ultraviolet. But not evenly across that range. The Frank-Tamm formula, the quantitative theory that Ilya Frank and Igor Tamm worked out in 1937, tells us how much energy is emitted per unit of path length at each wavelength. And what it says is that the energy emitted per unit wavelength scales approximately as 1 over the wavelength squared. In other words, shorter wavelengths get more energy than longer ones. The shorter the wavelength, the more light is made. Think of it like this. If you imagine laying out the visible spectrum from red on the left to violet on the right, then continuing off the right edge into the ultraviolet, the Cherenkov emission keeps rising as you move from red toward violet and keeps rising further as you move from violet into the ultraviolet. More energy at shorter wavelengths. More photons toward the violet, even more beyond it in the ultraviolet where the eye cannot go. So the spectrum is climbing toward the short wavelength end. It piles up toward the violet and ultraviolet. Now your eye comes in, and your eye is not a perfect detector across all wavelengths. In daylight, your eye is most sensitive, somewhere in the green and yellow, but in dim conditions, like a reactor pool, where you are not flooding the scene with bright white light, but looking for a faint glow, your eye shifts its sensitivity a bit, and either way, the blue and violet end of the spectrum is where the Cherenkov emission is the most intense within the visible range. Most of the Cherenkov energy actually goes into the ultraviolet, which is completely invisible to you. But of the part that you can see, it is disproportionately in the blue and violet. The spectrum is a ramp that runs up through the visible and keeps going beyond it. Your eye catches the top of the visible ramp, which is the blue-violet end, and calls it blue. So the reason Cherenkov radiation looks blue is that it produces more light at shorter wavelengths, and the shortest wavelengths your eye can detect happen to be the blue and violet ones, and they are more intensely produced than the red and orange end. If you could see ultraviolet the way some insects can, you would see the glow even more intensely, and it would not look blue at all. It would look like a blaze of ultraviolet fire trailing through the water. But you can't. So blue it is. This is also why the glow in the reactor pool has that particular quality, a deep, almost cold blue, not a warm amber, not a soft green. It is not colored by a chemical, it is colored by a formula, by the mathematics of how coherent wave emission distributes energy across wavelengths when the geometry of a Mach cone is involved. The 1/wavelength squared relationship is baked into the physics of the cone, and the cone gives you that specific tilt toward the short end, and the short end is blue, and the spectrum is continuous. It does not have gaps. There is no signature of water in it, no characteristic atoms, no fingerprint of the fuel. You could, in principle, fill the pool with a completely different transparent liquid and get essentially the same spectrum, shifted slightly because the refractive index changes, but still rising toward the short wavelengths, still blue. The glow carries no information about the medium's chemistry. It carries information only about the particle's speed and the medium's refractive index, which, if you stay with that for a moment, is a remarkable thing. The color and shape of this light are set not by what the particle is made of, not by what the water is made of, but by the geometry of a wave catching up to the edge of itself, and the mathematics of how that geometry divides its energy across the spectrum. There is a tidiness to it, a cleanness, almost a beauty. Let me bring that together for you now, before we move on, because we have been building something in layers, and it is worth letting the whole picture rest in one place for a moment. We started with the particle moving through the water. We established that it has to be faster than the phase velocity of light in the medium, faster than c divided by n, and that in water, for an electron, this means carrying at least about 0.26 million electron volts of kinetic energy. The fission products in a reactor provide that easily. Below the threshold, nothing happens. Above it, the light begins. We built the cone from its components. Every point along the particle's path radiates a spherical wavelet. The particle, moving faster than those wavelets, outruns them and leaves them as a trail of expanding spheres behind it. All those spheres share a single tangent surface, a cone, where they arrive in phase, add together coherently, and produce organized, directed light. The cone is the wake. The wake is the same geometry as the sonic boom, the same geometry as the bow wave of a boat. The angle of the cone, the Cherenkov angle, is given by the cosine of theta equals 1/n times. In water, for a near light speed particle, that gives roughly 41 degrees. For slower particles, a narrower cone. Below threshold, no angle at all, because the mathematics refuses to give a real answer. And the color is blue, because the Frank-Tamm theory tells us that more energy goes to shorter wavelengths, a continuous spectrum rising as 1/wavelength squared toward the violet and ultraviolet, so the portion your eye can see is dominated by the blue-violet end of the visible range. The threshold, the cone, the angle, the color. 4 things that answer what the glow is and why it looks the way it does. And we have arrived at all 4 of them, slowly, carefully, and without inventing any physics. Everything here was worked out, piece by piece, by real people in real places, making real measurements over the course of a few intense years in the 1930s. Which is where we are headed next. But for now, wherever you are, let the image settle. There is a pool. In the pool there is a faint blue glow, continuous and steady, spreading out from the reactor core in all directions as the fast electrons from fission tear through the water faster than light can travel in that water. Each one trailing a perfect 41-degree cone of organized, coherent light behind it. The light bunched up toward the short wavelength end of the spectrum, toward the blue and violet and ultraviolet, invisible in most of its intensity but showing you its blue fringe, its cool electric hem, the part that your eye can catch. Not heat, not chemistry, not fluorescence, not the reactor fuel glowing. A wake, a shockwave of light, a Mach cone, made of photons rather than pressure, carrying within its angle the precise mathematical record of how fast the particle that made it was moving. There is a shape hidden in the glow, and the shape is a number, and the number is a speed. Let that sit. No rush. Because what we have built so far is the mechanism, the how and the why of the light itself. But there is a whole other chapter waiting, and it is the chapter that turns this from a beautiful physics fact into one of the most powerful scientific instruments that human beings have ever built. Because once you understand that the cone's angle is a speedometer, a question follows naturally and quietly. If this glow can tell you how fast something was moving, can it also tell you that something was there at all? Can it detect a particle you could not otherwise see? And the answer to that question is yes, radically, staggeringly yes. In ways that involve burying the equivalent of a cubic kilometre of ultra-clear Antarctic ice 2.5 kilometres beneath the surface of the South Pole, filling it with 10,000 eyes made of glass and electronics, and waiting for a ghost. But that is for when you are ready to go further. We have laid the foundation now, the threshold, the cone, the angle, the colour, and the foundation is solid. You understand what the blue actually is. You know it is a wake. You know the wake has a shape. You know the shape encodes a speed. And somewhere out there, in a pool of water or a cubic kilometre of ancient polar ice, or the fluid of an eye closed in the darkness above the atmosphere, this blue is happening right now, this moment, as particles that crossed a threshold are leaving their 41-degree calling cards, as the coherent light of their passing spreads outward from the invisible line of their path. As the spectrum tilts toward the short end, and the short end says blue. It is happening in the reactor pools at the national laboratories, steady and quiet under the cool water. It is happening in the deep ice of Antarctica, where a particle released by a neutrino interaction is crossing the threshold in ancient frozen water 1.5 miles below the polar surface, and making its faint blue flash for the sensors waiting in the dark around it. It is even, as we will come to, perhaps happening in the eye of an astronaut somewhere above the atmosphere, floating in the dark with closed eyes, watching flickers and streaks of blue-white light that nobody put there, that are made in the vitreous humour of the eye itself, by cosmic particles that crossed the threshold inside the living body. The light is everywhere. You just have to know what to look for, and now you know what to look for. So rest here for a moment. Let the image of the cone rest in your mind. The particle, the wavelets, the coherent surface, the blue shifted spectrum, the 41-degree angle. It is all one thing, one elegant, single thing. And when you are ready, we will follow the people who first found it. So let us follow them. Let us go back, not so very far back, to a city that was cold in winter and complicated in every season, to a laboratory where the equipment was modest and the questions were enormous, and where one quietly persistent man was staring at something that almost everyone else had already decided to ignore. The year is 1934, the city is Moscow, and the man's name is Pavel Alekseyevich Cherenkov. He is working at the Lebedev Physical Institute, which sits in a part of Moscow that has the particular quality of Soviet scientific institutions in that era: serious, a little worn, full of people who have chosen to spend their lives thinking carefully about how the world is put together. It is not a glamorous place. It is not a place built for glamour. It is a place built for attention. Cherenkov is working under the direction of Sergei Vavilov, a physicist who understands something important, that the most interesting things in science are often the things other people have stopped noticing. A faint blue glow in a liquid exposed to radiation is, by 1934, one of those things. It has been seen. It has been documented. It has been, mostly, set aside. Because everyone thinks they already know what it is. They think it is fluorescence. And here is what fluorescence is, so you have it clearly. When certain molecules absorb energy from light, from radiation, from anything energetic enough, their electrons jump to a higher state and then fall back down. And the falling releases light. The energy goes in, and some of it comes back out as a glow. It is a beautiful process. It is also extremely common. And it happens to be exactly what you would expect to see when you pour radiation into a liquid. The radiation hits the molecules fluoresce. You see a glow. It is the obvious answer, and the obvious answer, as Cherenkov was about to discover, was wrong. He was using gamma rays from radium, not the particles themselves, but the high-energy photons that radium throws off as it decays. He was watching what those gamma rays did when they passed through liquids. And there was always this faint blue glow. There was always this soft, quiet shimmer in the liquid that he was shining the rays into. The straightforward interpretation was right there, waiting. Fluorescence. Everything said fluorescence. The whole field said fluorescence. But Cherenkov had a careful mind. And a careful mind, when it looks at something everyone has already explained, does not just accept the explanation. It asks whether the explanation is actually true. So he tested it. The first test was directionality. Fluorescence, when you think about it, does not care which way it goes. If you have a molecule fluorescing, it re-emits its light in all directions at once, spreading outward from itself like a tiny lamp. It has no memory of which way the original energy came from. It just glows in every direction equally. But when Cherenkov looked carefully at the glow from his liquid samples, he found something that fluorescence should not be doing. The glow was not equal in all directions. It was stronger in some directions than in others. It had, in other words, a direction. It was going somewhere. It had a preference, which is the last thing fluorescence has. That was the first crack in the obvious explanation. The second test was polarization. When light is polarized, its electromagnetic waves are oscillating in a particular orientation rather than randomly in all directions. Fluorescence emits light that is unpolarized, or very nearly so, because the re-emitting molecules are randomly oriented and tumbling in all directions. Their emitted light comes out scrambled. But the blue light from Cherenkov's liquids was polarized. It had structure. The waves were lined up in a way that fluorescence cannot produce. That was the second crack. Two properties that fluorescence does not have. One glow that had them both. There was a third test. It was perhaps the most decisive. Fluorescence depends on the chemistry of the liquid. Different molecules fluoresce differently. Some glow green, some glow red, some barely glow at all. You can change the color and the intensity of a fluorescent glow simply by changing what is dissolved in the liquid or by changing the liquid itself. Fluorescence is a molecular property. The molecule matters. So Cherenkov tried different liquids. He changed the composition of what he was looking at. He varied what was dissolved in it. And the glow stayed the same. Not just similar, the same. The same color, the same directionality, the same intensity, regardless of what the liquid was made of. Sulfuric acid, water, other solutions. It did not matter. The glow did not change the way fluorescence would change. It simply persisted, steady and blue, as if it had no interest whatsoever in the molecules it was passing through. Because it didn't. This was the clean, definitive result. The glow was not a property of the liquid. It was not the liquid's molecules telling you something about themselves. It was something else entirely. Something that the liquid merely provided a home for. Something that was happening because of the radiation passing through, not because of the medium it was passing through. Pavel Cherenkov had done something that sounds straightforward when you describe it, but requires a particular kind of stubbornness to actually do. He had looked at the obvious answer, tested it carefully, and found it was wrong. And then he had kept looking. He published. He described the directionality, the polarization, the independence from composition. He described, with care and patience, a phenomenon that he did not yet have a theoretical explanation for. He had the data. He had the careful measurements. He did not have the theory that would make sense of them. He had the shape of something, but not the name of the thing, yet. And in doing this, he was doing a very old kind of science, the kind where you describe a phenomenon first, where you go very carefully from measurement to measurement, and you trust that if your measurements are right, the explanation will eventually follow. He was also, in a sense, completing a task that others had started and then stepped away from, because the blue glow had been seen before. It had been seen in the context of something far more famous by one of the most famous scientists of the previous generation. And it had not been explained, it had simply been noticed, and then left. Let's step back even further, briefly, to the end of the previous century. To the laboratories of Marie Curie. You know the name. Everyone knows the name. Marie Curie, born in Warsaw, trained in Paris, the discoverer of polonium and radium, the first person to win 2 Nobel Prizes in 2 different sciences, the most important experimental scientist of her era by almost any measure you care to apply. She spent years working directly with radium, concentrating it, isolating it, studying it, carrying it around in her pockets, storing it in her workshop. The notebooks she kept from those years are still radioactive today. You can visit them in archives in Paris, but you have to sign a waiver first. Curie and her colleagues noticed that radioactive solutions glowed. They noticed the blue luminescence around the concentrated radium preparations. It was strange and beautiful and a little eerie, and in the glow-saturated world of early radioactivity research, it was one of many glowing things, many strange lights. It was noticed, but it was not understood. And because it was not understood, it was categorized under the nearest available category, which was fluorescence, and then it was moved past. There were too many other questions, too many other experiments, too many other things requiring careful attention. The blue glow of radium solutions was real. It was recorded. And it was waiting. It waited for several decades. It waited through the whole early golden age of radioactivity research, through the discoveries of different radiation types, through the beginning of quantum mechanics, through the mapping of the atom. It waited, this faint blue shimmer that nobody had correctly explained. Until 1934. Until a quietly persistent man at the Lebedev Physical Institute in Moscow looked at it and decided he was going to find out what it actually was. By 1937, Cherenkov had what he needed from experiment. He had shown, conclusively, that the glow was not fluorescence, that it had direction and polarization and indifference to chemical composition, that it was a genuine phenomenon distinct from anything that had been catalogued before. What he did not yet have was why. The why came from two other men. Their names were Ilya Frank and Igor Tamm, and they were theorists rather than experimentalists, which means they lived in the world of mathematics rather than the world of equipment and radium samples. They were looking at Cherenkov's results and asking the question that theorists ask: what are the equations that produce this? They found them in 1937. What Frank and Tamm worked out was the full quantitative theory of the phenomenon that Cherenkov had discovered, the theory that is now called the Frank-Tamm formula, and that bears their names because they derived it. And what they derived was not just the qualitative picture of a Mach cone of light, not just the intuition of wavelet overlap, but the precise mathematical description of how much energy is radiated, at what angles, at what wavelengths. They showed why the directionality existed. They showed where the polarization came from. They showed why the composition of the liquid didn't matter. They showed, from first principles, the whole mechanism, the charged particle moving through the medium, polarizing the medium momentarily as it passed, the electromagnetic wake building up and radiating outward, the spectrum rising toward shorter wavelengths, the cone angle following from simple geometry in a way that could be precisely predicted and precisely measured. They showed, in other words, that all of Cherenkov's careful measurements made perfect sense. Not just rough sense, precise sense. The theory predicted the angle of the cone, and the measurements matched the prediction. The theory predicted the shape of the spectrum, and the measurements matched that too. The kind of agreement you get when you have gotten something genuinely right, when the mathematics is not an approximation of what is happening, but an accurate description of it. The Frank-Tamm formula was the theory that put a name to the thing. And in Russia, the phenomenon was always given a fuller name: Vavilov-Cherenkov radiation. Sergei Vavilov, Cherenkov's supervisor, was acknowledged in the Russian tradition as co-discoverer, or at least co-investigator. When Russian physicists spoke of this effect, they spoke of Vavilov and Cherenkov together, the pair of them, the director and the student, the one who pointed toward the dark water and the one who stared into it until it gave up its secret. The Western scientific community settled on Cherenkov radiation as the name in common use, but the fuller name persists in Russia to this day, a quiet correction offered to anyone who thinks this was a single-person discovery. For 21 years after 1937, the name Cherenkov was known in physics circles, the formula was known, the effect was studied and used and understood. And then the world outside those circles found out, because in 1958 the story was given its formal ending. The 1958 Nobel Prize in Physics was awarded to Pavel Alekseyevich Cherenkov, Ilya Frank, and Igor Tamm jointly for, and this is the exact language from the award, the discovery and the interpretation of the Cherenkov effect. Discovery and interpretation. That is a careful pairing. The discovery was Cherenkov's, the patient experiments, the directionality tests, the polarization measurements, the proof that it wasn't fluorescence. The interpretation was Frank and Tamm's, the mathematical theory that explained why the discovery made sense. 2 stages, 3 people, 1 Nobel Prize awarded for work that had been done over a decade earlier. And all 3 of them were alive to receive it. Tamm and Frank flew to Stockholm. Cherenkov flew to Stockholm. 3 men, 3 speeches, 1 blue glow. You sometimes read accounts of the Nobel that focus on the fairness question, did Vavilov deserve to be there? He died in 1951, 7 years before the award, and the Nobel is not given posthumously. It is one of the ways the Nobel sometimes misses the people who should have been in the room. But that is the Nobel's limitation, not the science's. The science was done by all of them, and the science, once done, did not sit still. Here is where we arrive at the turn I promised you, a long time back in this conversation, the open loop I set down when I said, this glow is not a curiosity. It is a machine. I meant that. Let me explain what kind of machine. To understand it, you need to spend a moment with one of the strangest particles in the universe. Strange not because it does strange things, though it does, but because it barely does anything at all. The particle is a neutrino. You may have heard of neutrinos. They are produced in enormous quantities by nuclear reactions, including the reactions inside the Sun and including the fission reactions inside a nuclear reactor. Every second, trillions of neutrinos pass through your body. Not around you. Through you. They pass through the chair you are lying in, through the floor, through the earth itself, from one side to the other and out the other side, as if nothing was there. This is because, for a neutrino, almost nothing is there. Neutrinos have no electric charge. They interact through only one of the 4 fundamental forces in a meaningful way. The weak nuclear force. And the weak force is extraordinarily short-ranged. A neutrino can cross the entire Earth without triggering a single interaction. It can cross a light year of solid lead and emerge on the other side almost certainly untouched. They are, in a very real sense, the ghost particles of physics. And yet we know they matter. They come from supernovae, from neutron stars, from the most violent events in the universe. They carry information about the deep interior of the Sun that light cannot carry. Because light bounces around inside the Sun for 100,000 years before escaping, while the neutrinos from the same reactions escape in seconds. They oscillate between types. Electron neutrinos becoming muon neutrinos, becoming tau neutrinos, in a way that requires them to have mass, which is itself a discovery that overturned a long-standing assumption in the standard model of particle physics. Neutrinos matter. But how do you detect something that passes through everything? The answer, or at least part of the answer, goes back to the blue glow. Here is the key. Neutrinos themselves produce no Cherenkov radiation. They have no electric charge. They do not polarize the medium. They do not leave a wake. A neutrino passing through the most perfect, crystal-clear water in the world does so in complete silence and complete darkness, radiometrically speaking, from end to end, without a single photon to mark its passage. But, very occasionally, rarely, but not never, a neutrino does interact with an atom. It triggers a weak force interaction that knocks a charged particle out of the atom, an electron, perhaps, or a muon, kicked out of its comfortable orbit by the sudden, rare collision. That charged particle inherits some of the neutrino's energy and momentum. It goes flying through the water. And if it has enough energy, which, given that the neutrino came from something energetic enough to make it quite often does, it exceeds the threshold. Its speed in the water crosses above the phase velocity of light in that medium. It breaks the speed limit that is actually breakable, and it starts laying down the cone. the blue flash appears. The Cherenkov cone expands outward through the water at precisely 41 degrees, carrying in its angle the speed of the particle that made it, and carrying in its direction the direction the particle was traveling, and carrying in the particle's direction the memory of the neutrino that kicked it free. The ghost particle does not leave a footprint, but it kicks a pebble as it passes, and the pebble leaves a footprint, and the footprint glows blue. What you need to do, if you want to catch neutrinos, is build a place large enough to contain enough target material that the pebble kicking happens with useful frequency. Because it almost never happens, and you need it to happen a lot to learn anything. And then you need to surround that target material with enough sensors to read the cone when it appears, to measure the ring or the flash, to determine the angle and the direction, to reconstruct from the blue light the path of the particle that made it, and from that path the path of the neutrino that started everything. This is not a metaphor. This is the actual method. This is how it is done. And to build a detector like this, you need a lot of transparent material, and you need a place to put it where the background noise of other particles, cosmic rays, natural radioactivity in rock, the ordinary particle weather of the surface world, is quiet enough that the rare neutrino signal can be heard above it. Which is why the detectors are underground, or deep in the ice, or deep under a mountain. Any direction you go that puts mass between the detector and the surface, you reduce the noise. The neutrinos don't care. They fly through the Earth from one side to the other and arrive at your detector with perfect ease. But the unwanted particles, the cosmic rays, the secondary particles, the surface noise, they are stopped by the rock and the soil and the ice above. You build it underground. You fill it with something transparent. You watch for the blue light. And somewhere beneath a mountain in Japan, there is a place where this is happening right now, while you rest. It is called Super Kamiokande, and it sits beneath Mount Ikeno, inside a carved-out cavern of remarkable size. You would not build it there for any other reason. You would not hollow out the inside of a mountain in Japan for any purpose that did not require this specific combination of depth and darkness and isolation from the particle noise of the surface. But for a neutrino detector, it is nearly perfect. Inside this carved cavern, there is a steel cylinder, and inside that cylinder there is water, not ordinary water, though ordinary water looks the same to the eye. This is ultra-pure water, water that has been filtered and deionized and purified to a degree that far exceeds the purity standards of drinking water or even medical water. Water from which essentially all dissolved minerals and gases and organic materials have been removed. Water that is transparent in a way that makes ordinary water seem slightly smoky by comparison. You could look into this water and see to distances that would astonish you. There is a great deal of it. About 50,000 tons. Surrounding this body of water, on the walls and floor and ceiling of the cylinder, there are roughly 11,000 photomultiplier tubes. A photomultiplier tube is a device for detecting single photons, individual particles of light. It works by using the photoelectric effect, the same effect Einstein explained in 1905, in which a photon striking a metal surface knocks out an electron. And then that electron is accelerated and multiplied until a single photon becomes a readable electrical signal. They are exquisitely sensitive. They see light that the human eye cannot see. They see a single photon in the dark and they report it. 11,000 of these eyes, all watching. 50,000 tons of the purest water in the world, waiting when a neutrino arrives, which happens. Given the enormous flux of neutrinos streaming through the Earth at all times, with useful regularity, it occasionally kicks a charged particle free. The particle rushes through the ultra-pure water. If it is fast enough, and it frequently is, the Cherenkov cone forms. The blue light radiates outward at 41 degrees from the particle's path, spreading in an expanding ring until it reaches the walls of the cylinder, and there the photomultiplier tubes see it. They see not a cone, but a ring. Because the sensors are on the wall rather than behind the particle, they see the intersection of the cone with the wall's curved surface, and that intersection is a circle, a ring of blue-white detections rippling outward from the point of impact. And the shape of that ring, the size of the ring, the timing of the light arriving at different sensors, all encode the information that was promised in the geometry. The direction of travel, the speed of the particle, the identity of the particle, because electrons and muons make slightly different ring shapes, slightly different patterns, and Super Kamiokande can tell them apart. From the ring, you reconstruct the particle. From the particle, you reconstruct the neutrino. This is the machine. This is what the blue glow is doing in a carved mountain in Japan right now, as you lie in the dark and let all of this settle gently over you. But if Super Kamiokande is remarkable, what is happening at the other end of the Earth is something else again. We are going to Antarctica. There is a station at the bottom of the world, at 90 degrees south latitude, at the geographic pole of the Earth's rotation, called the Amundsen-Scott South Pole Station. It is operated by the United States. It is one of the most remote, permanently staffed locations on the planet, a place where the sun circles the horizon for 6 months without setting, and then does not rise for 6 months. And where the cold is not merely cold, but something more severe than most human beings will ever experience. It is staffed by scientists and support personnel who choose, with full knowledge of what they are choosing, to be there. And below it, far below it, deep in the ice that has been accumulating at the South Pole for hundreds of thousands of years, there is something extraordinary. The ice at the South Pole is ancient. It is compressed. It is, at depth, extraordinarily clear. The bubbles of air that give ice its normal whiteness, the tiny trapped pockets that scatter light and make ice look opaque, have been squeezed out at these depths by the pressure of the ice above, thousands of meters of it pressing down on the layers below. What remains is ice that is transparent in a way almost nothing else is, ice through which Cherenkov light can travel for distances that would be impossible in ordinary frozen water. Someone, years ago, had an idea. The idea was this: if you need a large volume of clear, transparent material as your Cherenkov detector, and you need it to be isolated from surface noise, and you need it to be underground or under ice to quiet the background, why not use the ice itself? Why not use a cubic kilometre of it? A cubic kilometre, not a tank, not a cylinder, a cube, 1 kilometre on each side, of natural polar ice at depth, instrumented with sensors dropped through drill holes bored down through the ice from the surface. The result is called the Ice Cube Neutrino Observatory, and it is operated by the University of Wisconsin-Madison. The sensors are called digital optical modules. Each one is roughly the size of a basketball, packed with electronics, and each one contains a photomultiplier tube looking outward into the surrounding ice. They were lowered, one by one, on long cables into holes that were drilled by melting the ice with hot water. Each drill hole went down to about 2.5 kilometers beneath the surface. The ice around the sensors was allowed to refreeze, locking them permanently in place. There are roughly 5,160 of these digital optical modules on 86 strings, frozen into the ice from about 1.5 kilometers deep to about 2.5 kilometers deep. They are there now. Right now, as you read this, as you drift, they are hanging in ancient Antarctic ice in total darkness at -50 or -60 degrees Celsius at the surface, but insulated from the deepest cold by the kilometers of ice above them, waiting when a neutrino arrives at ice cube, and they arrive from all directions, because neutrinos from cosmic sources arrive from everywhere, including from the far side of the Earth. And when it occasionally triggers a charged particle in the ice, the Cherenkov cone forms in the ancient transparent ice. The blue flash travels through ice that is clear enough to propagate it for the distances needed. And the digital optical modules see it, some of them before others, and the difference in timing across the array tells you which way the cone was traveling, which tells you which way the particle was traveling, which tells you where in the sky the neutrino came from. Because when something in the distant universe, a black hole, an exploding star, a jet of matter from a galactic nucleus, produces a neutrino energetic enough to trigger ice cube, that neutrino flies across perhaps millions of light years and arrives at the South Pole and passes into the ice and, very rarely, kicks a particle free. And the Cherenkov cone points back, like a compass needle, toward the source. A kilometer of ice as a telescope that sees not light but the blue flash that marks the passage of the messengers from the most violent events in the universe. A telescope that operates in the dark, buried in frozen water at the bottom of the world, reading the ghosts by the wakes they leave. There is also the Sudbury Neutrino Observatory, SNOW, they call it in Canada, deep underground, which used heavy water rather than ordinary water as its medium. The SNOW collaboration used Cherenkov detection in its heavy water tank to make one of the most important measurements in recent physics, confirming that neutrinos oscillate between types, that electron neutrinos arriving from the Sun were partly converting into other types on their way, and that this oscillation required the neutrinos to have mass. Neutrinos having mass was not predicted by the original standard model. SNOW's result, read through the patterns of Cherenkov rings in heavy water, changed the model. And then there are the telescopes that look up rather than down. High-energy gamma rays arrive from the cosmos, individual photons of extraordinary energy, the most energetic light in the universe. When one of these gamma rays hits the upper atmosphere, it triggers a cascade of secondary particles that shower downward through the air. And in that shower, the charged particles are moving extremely fast through air, which is itself a transparent medium, with a refractive index only very slightly above 1, so that light in air travels only very slightly slower than in vacuum. The threshold for Cherenkov radiation in air is much higher than in water, because you need to beat a speed that is nearly c. But these gamma-ray-induced particles are energetic enough. They produce Cherenkov light in the atmosphere, a brief, faint, blue-white flash in the upper air, lasting only a nanosecond or two, pointing downward along the direction of the shower. Ground-based telescopes, arrays of large mirrors and sensitive cameras pointed at the sky, with names like Veritas and HESIS and Magic, sit in the mountains and the high deserts of the world and point upward, watching for these flashes. Not flashes of gamma rays, the atmosphere stops those, but the Cherenkov light that the gamma-ray shower produces in the air on its way down. The air is the detector. The atmosphere is the transparent medium. The faint blue flash in the upper air is the signal. And from the pattern of that flash, from its direction and its brightness and its shape, you can reconstruct the energy and direction of the gamma ray that triggered it. This is how we observe the high-energy gamma-ray universe. Not by detecting the gamma rays themselves, which the atmosphere intercepts, but by reading the Cherenkov light they leave in the atmosphere as they are stopped. The reactor pool, the Antarctic ice, the mountain cavern in Japan, the upper atmosphere above the mountain observatories. The medium changes. The principle does not. A charged particle crosses the threshold. The cone forms at the Cherenkov angle. The light encodes the speed and direction of its maker. The sensors read the light. And the light tells us something we could not otherwise know, about the speed of a particle, about the origin of a neutrino, about the source of a gamma ray, about the structures of the deep universe. This is the machine. This is what the blue glow was always waiting to become. And now you have it. The whole arc from Cherenkov's patient, experiments with radium in 1934, to the digital optical modules frozen into Antarctic ice 2.5 kilometers below the polar surface. The whole arc from a blue shimmer that everyone assumed was fluorescence to an instrument that reads the messengers from the most distant, violent events the universe has ever produced. It is one unbroken chain. The careful measurements of polarization, the independence from composition, the directional asymmetry that told Cherenkov that something was aimed, that the light had a direction it preferred, the theory that Frank-Tamm produced in 1937, the formula that bore their names, the cone angle that followed from simple geometry, and the refractive index. The Nobel Prize awarded in Stockholm in 1958 to 3 men who had done the work 2 decades earlier. And then the decades of building, of scaling up, of filling tanks and boring holes and freezing sensors into the oldest, clearest ice on Earth. The neutrino is a ghost. It passes through planets without touching them. But it leaves a wake, sometimes in the right medium, a barely there kick. A charged particle knocked free, a 41-degree cone of blue light spreading outward in the dark. And we built machines to read the wake. The glow in the reactor pool is part of this, the same glow, the same mechanism, the same cone, merely happening in an environment you can see. The pool is accessible and lit and photographed, and so the glow is the image everyone knows. But it is not the most interesting place the glow happens. The most interesting places are the places where the glow is faint beyond faint, where a single charged particle crosses a threshold in ice or water that is kept so pure it barely exists as a physical object, and makes a flash so brief and dim that it takes 11,000 photomultiplier tubes to catch it, or 5,000 sensors frozen into a cubic kilometer of polar ice. Those are the places where the wake is serving as a speedometer for ghosts. And there are even stranger places where this light appears. Places you might not expect. Places rather closer than Antarctica, or Japan, or the high desert above the tree line. We said earlier that you may have already seen this light with your own eyes. Closed, we are almost there. But for now, stay with the detectors for a moment. Stay with the image of Ice Cube, with those 5,000 sensors in the ancient dark Antarctic ice, watching for the blue flash that marks a neutrino's passing. It is a quiet image in its way. All that silence, all that dark, all that cold, and in it these small electronic eyes, waiting. The particle comes from somewhere across the universe. It crosses distances we cannot properly imagine, in time we cannot properly imagine, and it arrives at the South Pole and enters the ice and encounters, against all probability, an atom. And the atom kicks free an electron, and the electron rushes through the ice, and the light forms at 41 degrees. And the sensors in the dark begin to fire, one after another, as the blue expands through the ancient frozen water toward them. This is happening. Somewhere in the ice below the Amundsen-Scott South Pole Station, as you lie wherever you are lying, this is happening. The ice is full of it. The universe is full of neutrinos, and some of them are triggering events in the ice right now, and the digital optical modules are recording blue flashes, and the data is flowing up the cables to the computers on the surface, and the computers are reconstructing cones and directions and energies, and somewhere in that data stream is the origin point of a particle that was produced in a cataclysm, billions of light years away. The blue glow is not a curiosity, it is a machine. And the machine is running, and there is another machine. On the other side of the planet, from where Ice Cube listens in its Antarctic dark, buried under a different kind of mountain, sits a different kind of eye. Under Mount Ikano in Japan, carved out of solid rock, there is a chamber, and inside that chamber is a tank. And the tank holds approximately 50,000 tons of water. 50,000 tons. Try to hold that number for a moment. Not 50,000 glasses. Not 50,000 bathtubs. 50,000 tons of water, ultra-pure, filtered to a degree of cleanliness that barely exists anywhere else on Earth, so transparent that light can travel through it for dozens of meters before the water begins to dim it. A lake, essentially. An indoor lake in a mountain. And around that lake, covering its walls and floor and ceiling, bolted to every surface like the compound eyes of some enormous insect, there are approximately 11,000 photomultiplier tubes. A photomultiplier tube is a device for seeing single photons, individual quanta of light. One photon arrives, strikes a surface inside the tube, and knocks loose one electron, and that electron is accelerated and multiplied through a cascade of surfaces until one photon has become a measurable pulse of current. It is, in the most literal sense, a machine for seeing the unseeable, and there are roughly 11,000 of them looking inward, into the water, from every angle. This is Super Kamiokande. It has been operating in various configurations since 1996. It sits under about a kilometre of rock, which serves the same purpose as Ice Cube's 2.5 kilometres of ice. It filters out the ordinary cosmic ray muons that would otherwise flood the detector and make every real signal impossible to find. The rock is a veto. Let only the things that can pass through a mountain through. Muons, mostly, can't. Neutrinos, mostly, can. And when a neutrino arrives at Super Kamiokande, which happens all the time because neutrinos pass through the entire Earth at essentially the speed of light, and the planet might as well be made of nothing to them. Very occasionally, one of those neutrinos interacts with a water molecule. It strikes a proton or a neutron or an electron inside the atoms of the water, and it transfers its energy, and it kicks a charged particle free, an electron or a muon, and that particle moves through the water faster than light moves through the water. And the cone forms, the Cherenkov cone, and the light fans outward at about 41 degrees from the particle's direction of travel, expanding as the particle moves. And it washes across the photomultiplier tubes on the far wall of the detector in a ring. Not a cone when you look at the wall, a ring. Because when the cone of light, a three-dimensional cone spreading outward from a single moving point, intersects a flat surface, the way a cone intersects a plane, it makes an ellipse, or, when it hits at the right angle, a circle. A ring of blue light, and each photomultiplier tube that the ring passes over fires its pulse, and the timing of each pulse, microsecond by microsecond, allows the computers above to reconstruct where the cone was coming from and what angle it was making, which tells them the speed of the particle that made it, which tells them the energy of the neutrino that made the particle, and which direction it came from. The ring is the readout. The ring is the data. And the shape of the ring, its sharpness, its spread, tells physicists something else. Electrons, when they move through water, tend to scatter slightly, and the Cherenkov rings they make are a little blurry, a little diffuse, a smear of blue. Muons are heavier and scatter less, and their rings are crisp. So Super Kamiokande doesn't just see neutrinos. It can tell you what kind of neutrino it was, an electron neutrino or a muon neutrino, by the clarity of the ring the interaction left behind. This matters. It matters enormously. Because for a long time, for most of the 20th century, physicists were not certain that neutrinos had any mass at all. The Standard Model, in its original form, predicted they were massless, travelling at exactly the speed of light, ghost-like not just in their indifference to ordinary matter, but in their weightlessness. And then a puzzle emerged. The Sun should produce enormous numbers of electron neutrinos as it burns, and the detectors on Earth were finding too few. Not slightly, fewer. About a third of what was expected. This became known as the solar neutrino problem, and it sat there unexplained for decades, and then Super Kamiokande and its data began to fill in the picture. And then the Sudbury Neutrino Observatory in a nickel mine in Ontario, Canada, provided the answer. The Sudbury Neutrino Observatory, SNO, was different from Super Kamiokande in one key way. It used heavy water, not ordinary water, where the hydrogen atoms carry one proton each, but deuterium oxide, where each hydrogen atom carries both a proton and a neutron. Heavy water responds to neutrinos in ways that ordinary water does not, and specifically it can detect all three types of neutrinos, electron, muon, and tau, while also being sensitive to electron neutrinos alone, which meant it could compare the total neutrino count to the electron neutrino count in a way no earlier detector could. And what SNO found, reading Cherenkov rings in its heavy water, was that the total number of neutrinos arriving from the Sun was exactly what the models predicted. All of them were there. It was just that most of them were no longer electron neutrinos by the time they arrived. They had changed. They had oscillated. The technical word is neutrino oscillation, shifting their identity from one flavor to another during the journey from the Sun to the Earth. And a particle can only oscillate in this way if it has mass. A truly massless particle, travelling at exactly c, experiences no time passing and cannot change. So the Cherenkov rings in the heavy water of the Sudbury Neutrino Observatory didn't just solve the solar neutrino problem. They proved that neutrinos have mass. A tiny mass, inconceivably small, still not precisely known, but not zero. A property that the Standard Model had not anticipated. A hint that physics is larger than the map physicists had drawn. This work was recognized with the Nobel Prize in Physics in 2015, awarded to Takaaki Kajita, who led the Super Kamiokande evidence for atmospheric neutrino oscillation, and Arthur MacDonald, who led the SNO result. The Cherenkov effect was the measurement instrument for both. So we have now a pattern. We have ice cube in the ice, super kamiokande in the water, snow in the heavy water, each of them reading the blue cone or the blue ring that a charged particle traces through a transparent medium. Each of them using that geometry, that specific angle, that 41 degrees, as a tool of extraordinary precision. But I want to tell you about one more kind of Cherenkov detector, because it uses a medium you might not expect. It uses the air. High above your head, dozens of kilometers up, where the atmosphere thins to almost nothing, cosmic rays arrive from space. Cosmic rays are charged particles, protons, helium nuclei, the nuclei of heavier atoms, sometimes moving with enormous energies, energies we cannot recreate in any particle accelerator we have built. And when one of these high-energy particles, or a high-energy gamma ray from a distant astronomical source, hits the upper atmosphere, it does not pass through silently. It collides with atoms in the air and produces a cascade, a shower of secondary particles that fan outward as they descend, a cone of charged particles spreading through the thin air above the mountain. And some of those particles are moving through the air faster than light moves through the air. Air has a refractive index too. It is very close to 1, almost 1, because air is so thin. But not exactly 1. The refractive index of air at sea level is about 1.0003. Tiny, but enough. Enough that a very fast particle can exceed the phase velocity of light in air. And when it does, the Cherenkov light forms at a very shallow angle, because the refractive index is so close to 1 that the threshold is very high and the cone is nearly flat. The flash is brief and extremely faint, but it is there. And on mountain tops in several places on Earth, there are telescope arrays specifically designed to catch it. Telescopes that point not at ordinary starlight, but at the faint Cherenkov flash that a particle shower paints across the upper atmosphere for a few nanoseconds. Veritas in Arizona, HESS in Namibia, Magic in the Canary Islands on La Palma, each of them looking up at the atmosphere as if the sky itself were a detector medium, catching the brief blue shimmer of a particle shower in the upper air and using its Cherenkov geometry to reconstruct the energy and direction of the original cosmic particle or gamma ray. The universe, in this way, is full of Cherenkov light. It happens in water, it happens in ice, it happens in heavy water, it happens in the atmosphere. It happens wherever there is a transparent medium and a particle fast enough to outrun the local speed of light. It is an extraordinarily common phenomenon once you know to look for it. And it turns out you may have even seen it yourself. Not in a reactor pool, not in a mountain detector, in the dark, behind your closed eyes. This is perhaps the most intimate thing I will tell you tonight, so stay with it for a moment. Since the Apollo missions, since human beings first left the protection of Earth's magnetic field and travelled into deep space, astronauts have reported a persistent and strange experience. In the dark of the spacecraft, with their eyes closed, trying to sleep or rest, they see things. Brief flashes of light, streaks like dim shooting stars crossing the visual field, patterns that appear and dissolve, not hallucinations in the ordinary sense, not complex images or dreamlike sequences, just brief, quiet, luminous events in the dark of closed eyes, in a place where there is no light source to explain them. The cause is cosmic rays. In the safe shelter of Earth's magnetic field and its lower atmosphere, we are largely protected from the high-energy particles that travel freely through space. Astronauts in orbit or beyond are not. The particles arrive and pass through the spacecraft walls and pass through the astronauts themselves. And as they pass through the eye, they interact. One of the leading proposed mechanisms, carefully, here, because it is a leading explanation rather than a fully settled one, is Cherenkov radiation in the vitreous humor, the transparent gel that fills the interior of the eyeball. A fast cosmic ray particle enters the eye, and if it is moving through the vitreous faster than light moves through the vitreous, it emits a Cherenkov cone. And that cone of light reaches the retina, and the retina, not knowing the difference between Cherenkov light and any other light, fires, you see a flash. Not because something is wrong with your eyes, not because you are dreaming, but because a particle from a supernova or a distant galaxy passed through the jelly of your eye and broke the speed limit of light inside it, and left a small blue wake. This is also debated. Direct ionization of the retina by the particle itself is another competing mechanism, and the relative contribution of the two effects is still being worked out. But the Cherenkov hypothesis is real, supported, taken seriously by the people who study it. And there is something about it that I find quietly extraordinary. That the same mechanism at work in a kilometre of Antarctic ice, the same cone geometry, the same 41 degrees, the same physics of a particle outrunning the phase velocity of light in a medium, that the same thing might happen, in miniature, in the transparent centre of a human eye as a cosmic particle passes through. The universe writes the same equation everywhere. But I did promise you one more thing, one harder thing. And I want to handle it gently, because it belongs in this story and it belongs in this night, but it is not a cheerful thing. There is a way to produce an enormous surge of Cherenkov radiation very quickly, not in a careful, controlled detector, not in the placid blue glow of a reactor pool, but in the first fraction of a second of a nuclear accident, when a fissile mass suddenly reaches criticality and the chain reaction runs away, uncontrolled, for a moment before it disrupts itself. In the instant of a criticality excursion, there is a flash, a blue flash or a blue-white flash, described consistently by the people who survived being near enough to see it and far enough away to live. At Los Alamos, in August of 1945, a physicist named Harry Daghlian was working alone at night with a mass of plutonium. He was building a neutron reflector around it, placing tungsten carbide blocks to reflect neutrons back into the core, incrementally raising its reactivity. He placed one block too many. The assembly went critical. He saw the blue flash and felt the heat of the radiation on his hands and face, and he knocked the block away, stopping the reaction, saving others, but not himself. He died 25 days later. 8 months after that, in May of 1946, the same piece of plutonium, the sphere that came to be called the Demon Core, was at the centre of another experiment. Louis Slotin was demonstrating a procedure to colleagues, lowering a beryllium hemisphere over the core with a screwdriver as the only thing preventing them from touching. The screwdriver slipped. The hemispheres closed. The assembly went critical. There was a blue flash and a wave of heat, and Slotin pulled the hemisphere apart with his bare hands, ending the excursion. He saved the people in the room by absorbing the bulk of the radiation himself. He died 9 days later. I tell you this not to frighten you, and not to steer us into disaster story territory, because that is not what this night is about. I tell you because the blue flash in that room is this same light. It is debated, as with the astronaut flashes, two mechanisms compete, and they are not mutually exclusive. The air itself, ionized so intensely by the radiation burst, may have fluoresced blue-white, charged atoms returning to their ground state and emitting light. And the observers close to the event, their eyes, may have seen Cherenkov radiation made within the fluid of their own eyes by the burst of fast particles. The physicists who study these accidents believe both mechanisms likely contributed. It is not clean. It is not settled. But the blue flash is there in the testimonies. It appears in the accounts of both accidents, described by the people who were present, and it is, in some terrible and exact way, this same glow, the wake of particles moving faster than light in a medium, read by the eye's own transparent gel, the geometry of Cherenkov enacting itself in the worst possible context. The blue light of a reactor pool is calm and beautiful. The blue flash of a criticality accident is neither of those things, but they share a physics, the same equation, the same threshold, the same angle. The universe does not adjust its rules for the occasion. I want to leave that quietly there and come back to something gentler. Because I told you earlier, in the very first moments of this journey tonight, that this glow is not what you thought. And I want to make sure you have everything you need to understand what it actually is. Here is a small correction worth making before we close. When you look at that photograph of the reactor pool, the one you have probably seen, the blue light rippling through the water above the submerged fuel assemblies, it might seem as though the glow is the reactor's power, as though the light is some fraction of the energy being released, as though what you are seeing is the heat of fission made visible. It is not. The Cherenkov radiation carries away only a tiny fraction of a particle's energy. A minute fraction. The light is a byproduct, a diagnostic, the whisper of something happening rather than the thing itself. The reactor's heat, the heat that boils water and drives turbines and produces electricity, comes from fission and from radioactive decay. The Cherenkov glow contributes essentially nothing to any of that. It is a side effect, a footnote in the energy budget. Beautiful, yes, informative, enormously. The geometry of the cone is a direct measurement of the particle's speed. But it is not the engine. It is the shadow of the engine. And there is one final thing I want to close the loop on, before we come all the way back to where we started. Earlier in the night I told you there were two scenarios, two possible worlds that this phenomenon shows us. One world where the cosmic speed limit stands unchallenged, where nothing with mass can reach c in vacuum, where the rule holds everywhere and always, and where Cherenkov radiation is therefore impossible by definition, because producing it would require the particle to exceed not just light speed in a medium, but the absolute limit. In a vacuum, where the refractive index n equals exactly 1, the phase velocity of light is c itself. There is no slower version of light to outrun. The threshold condition, v must be greater than c divided by n, becomes v must be greater than c, and nothing with mass can satisfy that. The door is closed. The effect exists only because of the second world, the world of materials, of transparent media, of glass and water and ice and air and the vitreous of the eye. In these materials, light slows, and a charged particle, carrying its kinetic energy from a reactor or a cosmic ray collision, is under no obligation to slow with it. It moves as fast as its energy allows, and sometimes, often, easily, at modest energies, that is faster than the local light. And when it is, the medium does what the medium does. The polarization wave spreads, the wavelets pile up, the cone forms. The light fans outward at a precise angle that encodes the particle's speed in its geometry, the way a ship's wake encodes the ship's speed in the angle of the spreading waves. The spectrum rises toward the ultraviolet, and the eye reads it as blue. And the blue glow fills the reactor pool, and the ring forms in Super Kamiokandé's 50,000 tons of water, and the digital optical modules in Ice Cube fire one after another in the ancient Antarctic dark, and the telescopes on the mountaintops catch the faint shimmer of a particle cascade in the upper air, and the astronaut sees a streak behind closed eyes. And the cone carries all of it in one number, one angle, the cosine of 41 degrees in water, the exact measure of how fast something was going when it made this light. Two scenarios. One where vacuum rules and the effect is forbidden. One where a medium is present and the local speed of light is beatable, and the wake appears, and the wake is a clock and a ruler and a speedometer all at once. Both are true. Simultaneously, the same universe contains both. And now I want to bring you back. Because when we started tonight, however long ago that was, wherever you are in this night, whether you are still fully awake or half adrift already, we started with a question. A simple question about a photograph, a blue glow in the water above a reactor core, and the feeling of looking at it and not quite knowing what you were looking at. The sense that you were seeing something that shouldn't be, something like a rule being broken. And we have come slowly through the whole long explanation, through 2 speeds of light and a refractive index and a threshold and a cone built from overlapping wavelets and a Nobel in 1958, and a cubic kilometre of ice and 11,000 photomultiplier tubes, and a mountain in Japan and a mine in Canada, and mountaintop telescopes in 3 countries, and the fluid of a human eye, and the terrible blue flash at Los Alamos, and the long quiet watches of Ice Cube in the polar dark. And the answer, when you hold it all at once, is this: nothing is breaking. Nothing was ever breaking. The rule, the deep rule, the cosmic one, the one that holds in every vacuum, in every direction, in every corner of the universe, that rule stands exactly as it always has. Nothing with mass reaches the speed of light in empty space. Not the particle in the reactor. Not the cosmic ray. Not anything. The rule is intact. But light is not always in empty space. Light is often in water, or ice, or glass, or air, and in those places light slows down. It slows down because it is interacting with the atoms of the medium, being absorbed and re-emitted, threading its way through a lattice of charged particles that delay it, and the speed it travels at is not c, but c divided by n, the refractive index. In water, it is about 3/4 of c, and a fast-charged particle carries so much kinetic energy that it moves through that same water faster than the light around it. Not faster than light, faster than this light, here, in this medium, right now. And the medium responds. It responds the way water responds to a boat moving faster than the water's surface waves, the way air responds to a jet moving faster than sound. With a wake, a cone, a shockwave of overlapping wavelets building up behind the leading edge of the disturbance. Only here, the disturbance is electric. The medium is polarizable. The wavelets are light, and the shockwave is Cherenkov radiation. The blue glow in the reactor pool is awake, just awake. The most beautiful, informative, quietly extraordinary wake in physics. A wake that encodes the speed of its maker in the angle of its cone. A wake that has taught us that neutrinos have mass. A wake that is right now, tonight, being read in a kilometre of ice below the coldest place on Earth, carrying messages from the most violent events in the universe. The light that looks like a broken law is not a broken law. It is what a law looks like when it meets the world exactly as it is, and I find that more satisfying than the broken version. because a broken law would just be chaos, an exception that explains nothing. But a law that holds everywhere, in every vacuum, that remains unchallenged even as particles in water outrun the local light. That is a law that knows exactly what it is. It is precise, it is bounded, it is real. And the glow in the water is not a hole in it, but a demonstration of it, a visible proof, in blue, that the universe runs by rules so exact and so generous that they allow for this exact phenomenon and no other. You have now seen that glow for what it is. And wherever you are tonight, and I find myself wondering, the way I always do at this point in a night like this, where exactly that is. Wherever you are, there are neutrinos passing through you. Through the mattress beneath you and the ceiling above you and the walls around you and through the planet below you. Right now, right through the whole Earth as though it were a window pane. Trillions of them every second, from the sun and from distant collapsing stars and from sources we haven't even identified yet. They pass through you without stopping, without caring, without leaving any trace. And some of them, tonight, are arriving at the ice below the South Pole and interacting with atoms in the deep frozen dark and making blue cones that the sensors are reading. And the data is flowing, and somewhere in it is a direction that points to something extraordinary. The glow is a machine. And the machine is running, right now, while you are perfectly still. You are embedded in this. Not watching it from outside. The neutrinos are passing through you. The cosmic rays are occasionally making brief blue flashes behind the eyes of astronauts. The same geometry, that cone, that angle, is being drawn in ice and water and air in detectors on every continent. You are in a universe that is saturated with this light, most of it invisible to you, all of it carrying information about the most extreme events in the cosmos. And now you know what it is. You can look at that photograph of the reactor pool, the one you have seen before, the one that started all of this, with the blue glow sitting in the water above the fuel, and you can see it correctly. Not as a glow of danger, not as the reactor's power made visible, not as a broken rule or a radioactive shimmer or anything mysterious. You can see it as a wake, a shockwave of light built from overlapping wavelets, fanning outward at a cone angle whose cosine is 1 over the refractive index times the particle's speed as a fraction of c, rising in brightness toward the ultraviolet, perceived by your eye as that deep, particular, characteristic blue. You can see the geometry in it. And the geometry is a measurement. That is what it was, the whole time. I hope this night has given you something to carry into sleep. Not worry, not complexity, just the quiet satisfaction of a thing that seemed mysterious, turning out to be exactly as deep as it appeared, and exactly as orderly. The universe is like that, when you look at it slowly enough. Not chaos underneath the surface. Just more precision, more elegance, more structure than you could see at first. And the blue light in the water is one of the clearest examples of it. If you enjoyed this slow journey tonight, and I hope you did, or at least that it gave your mind something soft to rest on, a gentle like or subscribe helps this sleepy little channel keep going. Small creators like me truly rely on your support to keep these long, quiet nights of explanation coming. And I'd love to know, where in the world are you watching from, and what time is it in your corner of the night? Leave me a note when you wake up if you remember. Sleep well, fellow voyager. The next journey keeps until you wake.